Hey guys, so continuing on from the last video, we're looking at the point of action of the resultant force. So going back to our diagram from the previous video, we're going to be trying to find our YR. So in this diagram, we haven't yet proven whether YC and YR are different. It is slightly intuitive to think that FR will be acting through the centroid of the surface that we're considering. This is not the case. I'll prove that to you through this derivation. So we'll be trying to find YR. So considering the moment of FR about the x-axis, we'll have FR times YR. And this will be equal to the moment of the distributed force about the x-axis. So we'll compare the two. So FR times YR will equal the integral of A y times df. In the previous video, when trying to derive FR, we had this equation here. Now that we're trying to find YR, we're going to compare this here. So that's the moment of the distributed pressure force about the x-axis, and that's the considering the moment of FR about the x-axis. So we're going to sub in P dot dA for the dF there, as we did in the previous video. So we'll integrate it in a similar fashion. So we're just going to make these substitutions. And h here will equal y sine theta. So we'll get y squared sine theta dA. And if we take out the constants, we're left with integral A y squared dA. So that's looking pretty similar to the derivation of FR, except that here we've got y squared, which is in fact the second moment of area. So we know that FR equals specific weight times YC sine theta A. Now that we're multiplying by YR, that will be the solution to that. And we're going to compare that to what we found above. We're going to cancel out the specific weight, the sine theta, and simplify. We want to find YR here, so we're going to rearrange that so we have YR on one side and everything else on the other. So YR equals YC A integral of y squared across the area A. So that's our equation for YR. So y squared dA, we said that was the second moment of area.